Hi, my name is Daniel Sishi, and my final year project is real-time ball tracking for soccer coaching. The goal of this project is to design and implement a low-cost coaching aid used to develop the shooting and passing of community-level players. A bit of context. I started playing soccer at 8 years old. However, since the age of 16, I have been coaching. I currently hold the Football Federation of Victoria's highest level of community-level coaching accreditation, where I focus on the 4 core skills outlined in the National Football Curriculum set out by the Football Federation of Australia. One of those skills, striking the ball, consists of shooting and passing, both of which will form the basis of this project. The motivation behind this project is to develop the future of Australian football through the use of technology, as the Football Federation of Australia has not considered its use in its national football curriculum. The project objectives are separated into core and minor objectives. The core objectives include tracking a football into the goal at a speed of up to 20.74 meters per second at a frame rate of 15 frames per second within 20% error within 75% of the time. The device needs to be powered by a portable power source and must not have any sharp edges to prevent injuries. The minor objectives of this project include signaling the coach that the football has entered the goal with basic accuracy within 1 meter in real time within 3 seconds. Displaying the accuracy of the ball using a green, yellow, and red scale using LEDs. And integrating a PSOC to determine the speed of the football up to 20.74 meters per second and indicate if the football was traveling too fast. The approach taken in this project was to enhance a pre-existing ball tracking algorithm by implementing an extended Kalman filter to better predict the location of the football, and to integrate the software with low-cost hardware in order to develop the device which is safe for use around children. Firstly, the software. The algorithm works by color filtering each video frame in order to identify the football. It then proceeds to locate and track its center point. The extended Kalman filter predicts the location of the football based on its previously known position. The extended Kalman filter predicts the final location of the football in the goal, given the camera cannot track the ball into the goal, and flashes LEDs according to the accuracy in terms of pixels from the target location. Given the pre-existing code was written in Python, it was decided to continue using it. The advantages of Python include it being a high-level language which is object-oriented. This allows for easy debugging as the code is organized according to class and function. Additionally, there are many libraries available to be used through Python, an example of which is NumPy, which enabled me to effectively utilize matrix manipulation to develop the extended Kalman filter. Finally, Python is compatible with OpenCV, an open source computer vision library which enabled the color filtering and morphological transformations necessary to track the ball. The pre-existing code was used to track a green ball and used a contrail from the center of the ball to track its trajectory. Changing from a green to an orange ball resulted in several issues, one of which was the ball tracking itself. As is evident, my nose was incorrectly misidentified as the ball. This called into question the robustness of the code. To fix the robustness issues of the pre-existing code, it was decided to investigate the color filtering. The color filtering relied on constructing a mask, where only the orange object was able to be extracted from each frame, effectively forming a blob. A morphological transformation called erosion was applied to the mask. Erosion removes small white noise from the mask, however, it also blurs the edges of the ball. As a result, the ball could often not be identified in the mask, as the blob, created from the color filtering, did not form a circular shape. This issue was remedied in the final implementation of the code, as the mask underwent a morphological transformation known as opening. Opening is a combination of erosion and dilation, its effective opposite. Therefore, by applying erosion, all small white noise was removed. However, by using dilation, the edge was detected as it effectively reverses the edge blurring associated with erosion. Next came the development of the extended Kalman filter. The extended Kalman filter implemented in this project relies on a constant velocity assumption. This constant velocity assumption allows for the linearization of the non-linear movement of the ball. This in turn is used to predict its location based on its previously known state. When first tested, the Kalman filter initially overshot the trajectory of a theoretical ball. However, this was quickly rectified to perfectly match the trajectory and was subsequently integrated with the ball tracking algorithm. When first integrated, the frames used by the Kalman filter to predict the next location of the ball were off sync with the ones currently being displayed. This resulted in overshooting. The frames displayed were subsequently delayed by one frame in order to rectify this. Next came the hardware. The Raspberry Pi Model 3B Plus was chosen as the computer in this project as it is cheap, small and powerful. It is fully compatible with the Raspberry Pi 5-megapixel camera, which reduces computational time, and can power the electrical circuit via its GPIO pins. Additionally, a Python environment comes pre-installed on the Raspberry Pi. This allows for coding directly onto the device. Finally, a 20,000 mAh portable lithium-ion battery was selected so the device can be powered for up to 8 hours off one charge, more than sufficient for several back-to-back trainings. The initial approach in this project was to use stereoscopic processing via a camera multiplexer to track the ball. This would have allowed the distance of the ball from the camera to be calculated in real time. However, this approach was abandoned as successive frames would be corrupted when the cameras were multiplexed. As a result, it was decided to use one camera, as the combined algorithm was operational with just one camera. This approach subsequently reduced computational time further and effectively simplified the process. The push buttons and LEDs were soldered onto VeroBoard to improve the user interface. This allows the coach to interact directly with the device and receive feedback. A plastic junction box and Velcro straps were used to form the housing unit. This was done so the unit could be safe around children, as there are no sharp edges, it is waterproof, and it can be easily removed without the use of tools. Next came the final implementation. Seen here, the device was tested by passing the ball into the red passing zone. This indicates a poor pass. The observed result was corroborated by the independent tester, who could see both the LEDs on the side of the unit and the color printed to the Raspberry Pi console. Similarly, here the ball was aimed at the yellow passing zone. This indicates a moderately accurate pass. The Kalman filter predicted the ball would enter the yellow zone, and as seen in the console, it successfully predicted the final position of the ball. Following this, the results of the testing were determined. In terms of meeting the core objectives, the football was successfully tracked at 9.76 meters per second, at 14.3 frames per second, over 80% of the time at an accuracy of 20 pixels. It was successfully powered by a portable power source, and the housing unit does not have any sharp edges. In terms of the minor objectives, the device successfully signaled the coach that the football had entered the goal, with the accuracy given in terms of the Euclidean distance of pixels. It successfully displayed the accuracy using a red, yellow, and green scale via the LEDs. However, the PSOC was not integrated given time constraints. In reviewing these results, the ball speed and frame rate values are lower than aimed for in the core objectives. These values are due to computationally heavy functions. These functions, namely the ball identification function, which uses morphological transformations, and the extended Kalman filter, which is used to predict the location of the ball, are constantly running to ensure the ball is always tracked. This ultimately affects the rate at which the camera can retrieve frames, a reduction of the frame rate. This reduction in frame rate affects the speed at which the ball can be tracked between frames. However, given this is to be implemented at a community level club, these results are more than satisfactory, as children will not be reaching such shooting or passing speeds. I have proposed some potential future areas to explore for this device. Integrating an LCD screen to display the speed or the accuracy of the pass or shot. This would improve the feedback a coach could give. Develop an app to control the device via Bluetooth, again simplifying the process. Utilizing an adaptive color filter to change the color of the ball wishing to be tracked. Using a camera with a wider lens and higher frame rate to track the ball better. Using a smaller portable battery to make the system more compact.
Astonishing! It's absolutely